Good morning students, this is next topic, that is screening effect. One more name for this is shielding effect. Here the definition is, see, this is nucleus, this is first shell, second shell, third shell. We know that in all shells electrons are present. Here the point is, if the electrons are present in first shell, then those electrons having more attraction towards nucleus. If electrons are present in second shell, then those electrons also having attraction towards nucleus, but its attraction is somehow less compared to the electrons present in first shell. If the electrons are present in third shell, those electrons also having attraction towards nucleus, but its attraction is very less compared to electrons present in second shell and third shell. Second shell and first shell. So what is the point here? Due to the presence of electrons in inner shells, due to the presence of electrons in inner shells, then the attraction between nucleus and outermost electrons decreases. That is called screening effect. One more name is shielding effect. Screening effect or shielding effect. So what is the definition? The attraction between nucleus and outermost electrons decreases due to the presence of electrons in inner shells. That is called shielding effect or screening effect. One more point, that is, if screening effect increases, that means screening effect increases means if electrons present in inner shells increases. That is the meaning of that one. If electrons present in inner shells increases, then the attraction between nucleus and valence electrons decreases. So what happened? If nuclear attraction decreases, then atomic size increases. I repeat once again. Screening effect increases means the electrons present in inner shells increases. Then automatically nuclear attraction decreases. Nuclear attraction means attraction between nucleus and valence electrons decreases. Then atomic size increases. If atomic size increases, IP decreases. We discussed already, between atomic size and IP inversely relation is there. So between screening effect and IP also inversely relation. So if the screening effect increases, IP decreases. So what is the point here? If electrons present in inner shell increases, then nuclear attraction decreases, then atomic size increases and IP decreases. That means the electrons present in inner shells acts as screens. The electrons present in inner shells acts as screens. That is why the nuclear attraction decreases. That is why this is called screening effect. This is about screening effect. Next topic is Next topic is electron affinity, ORR, electron gain enthalpy. Electron affinity, ORR, electron gain enthalpy. This is exactly opposite definition to IP. IP means what? We have to remove electron from outermost orbit when atom is in neutral, gaseous, isolated. That is called IP. Here the definition is exactly opposite to IP. That means here we have to add one electron when atom is in neutral, gaseous, isolated. Their energy is absorbed. Here energy is released. When electron added, energy is released. That is why this is called electron gain enthalpy. Enthalpy means energy. Electron gain means after addition of electron takes place, energy releases. That is why this is called electron affinity or electron gain enthalpy. So the definition is, the amount of energy is released when an electron is added to neutral, gaseous, isolated atom is called electron affinity. This is called electron affinity. See, this is the representation for given definition. See, this is neutral atom, that means this is having no charge. Next, this is present in gaseous state, and this is in isolated state. Isolated means single. When we add electron to that atom, then what happens? In previous video I discussed already, that is, if electrons are present in left side, that indicates what? Gaining of electrons, nothing but addition of electrons, then anions will be formed. Next, this is also called first electron affinity, because here we are adding one electron only. That is why this is also called first electron affinity. Here one important point is that is first electron affinity, nothing but EA1 is always exothermic, except in some cases, that is beryllium, magnesium, nitrogen and inert gases. That means when we add electron in these cases, their energy is absorbed instead of releasing energy, because beryllium, magnesium having what? Completely filled configuration. Nitrogen is stable configuration. Inert gas is already stable configuration. So in those configurations we cannot add electron easily. That is why their energy is absorbed instead of releasing. In these cases, except in these cases, remaining all cases, energy is releases. Next, second electron affinity. That means just like a second IP. That means to negative ion we should add one more electron. That is called second electron affinity. But here one point is there. See, this is negative ion, we should add electron. See, here negative charge is there, here negative charge is there. Between negative charges, but means between same charges, repulsions occur. To remove that repulsions, to overcome that repulsions, externally we apply some energy. That is, then those repulsions will be removed. Then addition of electrons takes place. Then energy is absorbed instead of releasing. So what is the point here? Second electron affinity is endothermic. Second electron affinity is endothermic. Why? I repeat once again. Here negative charges are present. Uni-negative ion. What is the meaning of second electron affinity? To uni-negative ion we should add an electron. Here what is the point? Between same charges, repulsions occur. To overcome that repulsions, to remove that repulsions, we should apply some energy. Then energy is absorbed. That is called second electron affinity. Then what about third electron affinity? Third electron affinity also same. That means to by negative ion we should add electron. There also same, between negative charges repulsions occur. There also we should apply some energy externally. There also energy is absorbed. So what is the point here? Except EA1, EA2, EA3, EA4 all are endothermic. EA1 is exothermic, but in these cases EA1 endothermic. So what is the definition of second EA2? The amount of energy is released. The amount of energy is absorbed with when an electron is added to uni-negative ion. When an electron is added to uni-negative ion. This is the represent equation regarding this statement. So EA2 is always endothermic because some energy is applied to avoid repulsions between addition of electrons and uni-negative ions. Next, EA3 also endothermic. No need to discuss about that one. Next, variation of EA in groups. Variation of EA in groups. That means in groups from top to bottom, EA decreases due to increase in atomic size. That means if the size of the atom increases, it is very difficult to add electron to such atoms. I repeat once again, if size of the atom increases, we cannot add electron easily to such atoms, thereby electron affinity decreases. That means if size of the atom decreases, then we can add electron easily, so that electron affinity increases. So what is the statement here? What is the conclusion here? If atomic size increases, Ea decreases. If atomic size decreases, Ea increases. So in any group atomic size increases, automatically Ea decreases. What is the statement? In groups from top to bottom, Ea decreases due to increase in atomic size. That's all. Next, variation of Ea in periods. In periods atomic size decreases, automatically Ea increases. So what is the statement? In periods from left to right, Ea increases. In periods from left to right, Ea increases due to decrease in atomic size. So this is about Ea. Next, here one exception is there, that is C. Chlorine has more electron affinity than fluorine due to less in size of fluorine. Stronger interelectronic repulsions takes place in fluorine. See, I will show one example. From that you can get clear idea. Here the point is fluorine present in second period, chlorine present in third period. That means from top to bottom what happened? Electron affinity decreases. But here one exception. Compared to second period elements, third period elements having more electron affinity, because second period elements having very less size, so that it is very difficult to add electrons, because second period contains 2p subshells, third period contains 3p subshells. So compared to 2p subshells, addition of electron very easily compared to 3p subshells, because 3p subshell is somehow large. So what is the point here? Compare all second period elements having less electron affinity compared to third period elements. That is exception. Actually second period elements should have more Em, but third period elements having more electron affinity. What is the reason? Due to less size of 2p subshell in fluorine and stronger interelectronic repulsions. That means what? Stronger interelectronic repulsions means repulsions forms between addition of electrons and existing electrons in atom. That is why those are called stronger interelectronic repulsions. Those repulsions are more. That is why we cannot add electron easily in case of second period elements. So second period elements having less Ea than third period elements. This is very important point. So this is the application. Chlorine belongs to third period, fluorine belongs to second period. So chlorine having more Ea than fluorine. That is the question. Next, the highest Ea is chlorine. Highest Ea in periodic table is chlorine, and the lowest Ea in periodic table is cesium, because cesium having more size, automatically it will be having less Ea. So this is about electron affinity.